Hey, welcome back for AP Chemistry. You're here with Mrs. Mays, and today we're going to study bond energy in covalent compounds. So buckle up, here we go. First of all, let's just discuss the covalent bond for a moment. A covalent bond is created by the forces that cause a group of atoms to behave as a unit. So they stick together for some reason, and we want to know, why would they do that? Well, the simplest answer is simply that atoms tend to achieve the lowest possible energy state, and by joining forces, by staying together, they can exist at a lower energy state than any of the atoms would be entirely on their own. So how does this work? Well, the truth about bonds is that a bond is simply a human invention. There is truthfully no such thing as a bond. It's just a way for us to explain the energy changes that are associated with forming molecules, because it's a model that we use to conceptualize how these atoms would join together. So when we draw a line and call it a bond, we don't really mean that there's something connecting the two atoms. But what we do know is that the orbitals in which the electrons exist get distorted when they come into close contact with one another, and it changes the shapes of their electron clouds so that the atoms can be at their lowest possible energy state. So let's consider the example of methane, CH4. It takes 1,652 kilojoules to dissociate 1 mole of methane into its ions, into the ions that it was formed from. Since hydrogen is hooked to the carbon, then if we just divide 1652 by 4, then we would get the average energy of 413 kilojoules per mole. So we would say that bond energy is 413 kilojoules per mole. However, it's not entirely true that every hydrogen is connected to the carbon with the same amount of energy. We made some simplifications in describing that bond energy. Each of those CH bonds would have a different kind of energy. For instance, if we look at the bond between the CH3 and the hydrogen, then that enthalpy change, the associated enthalpy, is 435 kilojoules per mole. But consider a hydrogen bond when it's only a CH2. Like if we took another hydrogen away from here, then you would have a higher energy associated with that bond energy. Now let's look at the next one. Take another hydrogen away, and now the bond energy is lower. And then if we're looking at just the one hydrogen and the one carbon, the bond energy is even lower than that. So when we were finding the average energy, then we're simplifying the case, which is okay to do, but realize each bond is sensitive to its environment. If there are more hydrogens around that carbon, then it's going to have a different amount of energy associated with it. So how do we use bond energies? Well, the easiest thing is that we often are asked to find the enthalpy change for a reaction. We can use bond energies to do that because it requires energy to break bonds and end up with atoms. Breaking bonds is going to cost us energy. Don't let a biology teacher convince you otherwise. It's going to cost us energy to break bonds and get the atoms out of the molecules. That's a positive energy change, right? And so we would classify this as endothermic. This is an endothermic change. On the other hand, when we use atoms to form bonds, it releases energy. So that would be an exothermic type of change. So forming bonds releases energy. Breaking bonds requires energy. And energy and enthalpy, recall, are state functions. So it doesn't matter how we add up to get the final reaction, because it's a state function. It matters where you start from and where you end up, not how you get there. So to find bond energy, here's what we're going to do. We find the sum of the bonds broken, Remember, we're breaking bonds on the reactant side, and subtract from that the sum of the bond enthalpies of the bonds that are formed when we make products. So we add all of these up, every bond that is formed, and subtract it from every bond that we had to break, and that will give us the overall energy change in that reaction. Let me show you how it's done. So we're going to find the energy change for this reaction, and we're going to draw some bonds here. Alright, then let's add up this reaction. So let's look at each of the bonds we have. First we have the carbon-carbon double bond, and then a carbon single bond. And on the ends I have here 2 hydrogens, and on the other end I have 3 hydrogens. So let's sketch those in. And in the middle, remember every carbon needs to have 4 bonds, so I've got 1 hydrogen sticking up here in the middle. Now there's 2 of these molecules, so all of these bonds are going to be doubled because I have 2 of everything. And I'm adding that to 2 ammonias, so let's draw the structure of ammonia. This one you should have memorized by now because we keep using it over and over. So here's my ammonia. There's 2 of those. And then there's the oxygen 2 molecule, which is a double bonded oxygen with 2 lone pairs on each oxygen atom. So there's our reactants. Let's add these up first. So in the first molecule, I have how many CH bonds? Let's count them up. Let me change my color so we can see. 1, 2, 3, 4, 5, 6. Alright, so I'm going to take 6 times the energy that is stored in that CH bond, 413 kilojoules per mole. 2,478 kilojoules per mole. Now let's look at the carbon bonds. First of all, I have a carbon-carbon double bond, and then I have a carbon-carbon single bond in this molecule, and there are 2 of them because of this. Oh, I forgot to double this. 2 times this means I have to double this. Ah, good thing I caught that. Alright, so here's my carbon-carbon double bond. 2 times 614 kilojoules per mole. And then my carbon-carbon single bond, I have 2 of those. And where's that one? Here it is, 347 kilojoules per mole. So, calculator time. So I have 4,956 from carbon and hydrogen bonds, 1,228 kilojoules per mole for my carbon-carbon double bonds, and 694 kilojoules per mole for the carbon-carbon single bond. There's that molecule done. Now let's look at the ammonia. In ammonia I have how many NH bonds? Let's see. There are 1, 2, 3 of those bonds, and we're going to double it because there's 2 of those molecules. So 2 times 3 times the NH bond is 391 kilojoules per mole. So let's add those all up. 6 times 391 is 2,346 kilojoules per mole from the ammonia. And our last one is the oxygen. So in the OO double bond, there's 1 molecule of oxygen and 1 bond between them for 495 kilojoules per mole. That's all of the reactants. We're going to add those up. So on the reactant side, what do we have? 9,719 kilojoules per mole is going to be what is required to break all of these bonds. That is a positive energy change because it takes energy to break bonds. Now let's look at the products. First we're going to sketch these out so that we know the molecular structures we're dealing with. So I have 2 CH2s, let me just draw the structure first here. CH2, CH, CN. Alright, so first I have a double bonded carbon, then a single bonded carbon that is triple bonded to a nitrogen. Remember, nitrogen loves to have 3 bonds, so we've got to give that guy a triple bond. Alright, now I have 2 hydrogens on this side, and then the central carbon needs another bond. Let's hang a hydrogen off of there. And then this carbon has 4 bonds, and nitrogen needs to have 4 bonds there, so we put that lone pair. And there's 2 of these molecules, so everything in here is going to get doubled. Don't let me forget. And then the water, you should be able to sketch that without any trouble, because we've done that over and over. So we have our bent molecular structure, 2 lone pairs on our oxygen, and there are 6 water molecules. So don't forget that everything in here is going to get multiplied by 6. Now let's add up all the energy in the products. So for the carbon to hydrogen bond, how many of those exist? 1, 2, 3, and we're going to double it. So that's 6 times 413 kilojoules per mole. And that total is 2,478 kilojoules per mole from the bond between carbon and hydrogen. Now let's count up the bonds that are carbon-carbon double bonds. There's just one of those right here. Yeah? So for my carbon-carbon double bond, there are 2 molecules with an bond energy of 614 kilojoules per mole that come from the carbon-carbon double bond. And that is 1,228 kilojoules per mole. Then the next one, let's look at the carbon-carbon single bond, this one. There's only 1 in this molecule, but we do have 2 molecules that are like that. So my carbon-carbon single bond is 2 times 347 kilojoules per mole. 694 kilojoules per mole. And what else is in our molecule? Alright, the CN triple bond. Let's count that one up. There's only 1 of them in the molecule, but we have 2 molecules that have it. So that's 891 kilojoules per mole per molecule for a total of 1,782 kilojoules per mole. And then finally, let's take care of water. The hydrogen to oxygen bond in the water is 1 on each side, so 2 of these in that molecule. And then there's 6 molecules like that, and that bond energy is 467 kilojoules per mole for a total of 5,604 kilojoules per mole from the water. Now let's add up the sum of the products. All the bond energy in the products adds up to be 11,486 kilojoules per mole, and since that's going to release energy, then that's going to be negative. That's why when we do bond energy, we take the sum of the bonds broken minus the sum of the bonds formed. So the reactants minus the products instead of products minus reactants, because this number is going to be endothermic, positive, and this number is exothermic, so it's going to be negative. So really all we're doing is adding up the total energy here, but it turns out to be reactants minus products because it's always exothermic when we form bonds. So we do 9,719 kilojoules per mole minus 11,486 kilojoules per mole. And that total is 1,767 kilojoules per mole for this entire reaction. So that's how we calculate the bond energy, or the overall energy change in a reaction using the bond energies. You've by now learned 4 ways to calculate delta H. The first one that we learned is Hess's Law, version 1, where we take the sum of the products minus the sum of the reactants. I just referred to that one a minute ago. The second version is the Hess's Law, where it's kind of like a puzzle. You add the reactions together to get an overall reaction in the end, where you could flip one or multiply by 2 or some other number. You remember doing Hess's Law puzzle problems. Then we could also use calorimetry, where you would have some number of kilojoules per mole, or if your energy is changing, it's Q equals mc delta T per mole, and calorimetry helps us to equate enthalpy to the heat that is gained or lost in the reaction. And then your fourth method is by bond energies, where you take the bonds broken minus the bonds formed. 4 ways to calculate delta H. You can expect to see all of these ways popping up in your exam and in this class. And that's it for bond energy. Keep practicing, and we'll see you soon.